Hello there. In this video, we'll be learning about limits at infinity. To start, as a motivation, we consider the function 1 over x. Let's try to check its value as x increases and decreases without bound. So we'll try to observe its value based on this table. Starting with this first table, observe that if we have x equals 1, so we'll have here 1 over 1 or simply 1. So we have this. If we have x equals 10, then we'll have 1 over 10, or this is 0.1 in decimal form. So we have 0.1 out. We continue this process until we complete this first table out here. Similarly, for this next table, if we plug in x equals -1, then we'll have 1 over -1. This would give us -1, and so we have -1 out here. For x equals -10, we have 1 over -10, or in decimal form, this is equal to -0.1. So we have -0.1. We continue this process until we complete this table. And let's try to make some observations. Observe that as x increases, f of x gets closer and closer to 0. Similarly, if x constantly decreases, f of x gets closer and closer to 0 as well. And to further understand this, let's try to check out the graph of f of x equals 1 over x. So let's have this and let's plot in the function. If we try to observe this part out here, so this is the part wherein x increases constantly, or x approaches positive infinity. So as x goes to positive infinity, although it's not quite noticeable in here, we have that its limit, or the limit of f of x as x approaches positive infinity out here, approaches 0, as we have seen out here. And similarly, if we check out the values out here, or as x approaches negative infinity, it gets closer and closer to 0 as well. So we have the limit of f of x as x approaches negative infinity to be 0. So this is what we'll be focusing on in this video. So we have limits at infinity. So essentially, limits at infinity are a type of limit wherein the value of x increases or decreases without bound. Or in other words, x out here approaches infinity or negative infinity. So as we have seen a while ago, this is what it looks like. So we have the limit of f of x as x approaches positive infinity to be L, or a certain limit. Again, what we mean by x approaching positive infinity is that x increases without bound. And similarly, for negative infinity, we have the limit of f of x as x approaches negative infinity to be L, or what this means out here is that x decreases without bound. So this is the idea on limits at infinity. Before we move on to our examples, we also discuss what a horizontal asymptote is. So when we say horizontal asymptote, to understand this, let's first focus on the word asymptote. When we say asymptote, what we mean by this is that this is a line that approaches a curve but never meets it, or approaches but never meets. So this is what you need to remember. Then if we add horizontal, since as we had said, asymptote is a line, then for horizontal, this means that horizontal asymptote is a horizontal line, and we know that horizontal lines are represented by the graph of y equals L. So this is the key point out here. If we combine these two, then we have horizontal asymptote to be the graph of y equals L, wherein, or such that, its limit, or the limit of f of x, or the curve f of x, as x approaches either positive infinity or negative infinity, is equal to L. So to understand this better, let's try to view it in a graph. So let's use the function that we had earlier. So we have f of x equals 1 over x. We know out here from a while ago that the limit as x approaches positive infinity, which is this side out here, of f of x is equal to 0. Similarly, the limit as x approaches negative infinity of f of x, or this one side out here, is equal to 0. So given this, we know that its horizontal asymptote must be given, or is given by y equals 0, which is this one out here. So essentially, the horizontal asymptote is a line wherein a graph gets closer and closer to it, but it never approaches it. So it's similar to the vertical asymptote that we had in infinite limits, but this time it is horizontal. So I hope that that one is clear. And now let's move on to some examples. So for our first example, we're tasked to find the limit of 1 over x squared as x approaches positive infinity and negative infinity. So before we answer and solve this one, feel free to pause the video so that you may try this one first on your own. Okay, good. So let's start. So in here, let's start to focus first on this first limit out here. So we have the limit as x approaches positive infinity of 1 over x. If we try to plug in positive infinity in this function, we'll have 1 over positive infinity squared. And what happens when we square a very, very, very large number? Say 99999, like that. Square this one, the outcome is still a very, very, very large number, even larger than this one. So a value that is even larger than positive infinity is just positive infinity as well. And as we seen a while ago, this is just equal to 0. But to explain that further, the idea here is that if we have, say, 1/2 out here, then we increase its denominator, say 1/3, 1/4, 1 over 5, and so on, till 1 over 100. We know that 1/2 is greater than 1/3, 1/3 is greater than 1/4, and so on, and so on. Since we know that this one is equal to 0.5, and this one out here, I think, let's move this, is equal to 0.01. So that is the idea behind this. Essentially, if we increase the denominator, if we keep on increasing it, the whole value of this fraction constantly decreases until it approaches 0. So the answer for the first item again is 0. Similarly, if we try to find the limit as x approaches negative infinity, so let's try to plug in that one, we'll have 1 over negative infinity, and let's square that one. In here, take note that if we square this, technically what we are doing is that we'll have -1 squared and infinity squared. We know that -1 squared is just equal to 1, and from above, if we square an infinity, it just becomes a very, very large number again. So we have here this. And again, this is just equal to 0. This out here is our final answer. In addition, if we try to find its horizontal asymptote, then we know that from these two, the horizontal asymptote of 1 over x squared is given by y equals 0. So take note of that one. And yeah, I hope you got this one correctly. Let's now move on to our next and final example. We have here the limit of x squared plus 2x as x approaches positive infinity, and the limit of 5x raised to 6 minus 4x raised to 4 plus 3 as x approaches negative infinity. Again, before we start, feel free to pause the video so that you may try this one on your own. Okay, good. So let's start. So let's start with the first limit out here. And let's try to plug in positive infinity. So we'll have positive infinity squared plus 2 times positive infinity and so on. Again, if we square a very, very large number, the outcome is just positive. And if we multiply a constant to a very, very, very large number, the outcome is still a very, very, very large number. So adding these two, if we add a positive infinity to a positive infinity, or we just add a very large number to another very, very large number, the outcome is just a even larger number, or just positive infinity as well. So we have this. So as simple as that. But how about this next one? So we have here again the limit of 5x raised to 6 minus 4x raised to 4 plus 3 as x approaches negative infinity. So if we try to plug in negative infinity in this function, we'll have this. And take note that if we raise a number, whatever that is, to an even exponent, we can basically remove the negative sign out here. So we remove this as well. And then if we multiply to a constant, we'll just have infinity out here. In here, multiply by a constant, we have infinity out here, and we have a plus 3 out here. But take note that the sign here is minus. So we'll have this. So basically, we'll have infinity minus infinity plus 3. But we know that from the previous video, infinity minus infinity is an indeterminate form. So we can't just plug in negative infinity out here. So what do? We learned that in the previous video that a strategy that we can use is we can try to convert this to in the form 0 over 0. But that only applies usually to a function that can be converted into a single fraction. So how do we do this? Well, here's a trick that we can use. So let's clear this one first. And take note that we can actually factor out x raised to 6 out here. So we'll have this one out here. So we have x raised to 6 times 5 minus 4 over x squared plus 3 over x raised to 6. If you're wondering where or how we obtained these two, well, take note that if we move this one out here, we'll have 4x raised to 6 over x squared. And by loss of exponents, we just subtract the exponents. So we'll have here 4 out here. Or 6 minus 2 is equal to 4. So this one is equal to 4x raised to 4, which is this one. And the same goes for the other one. So now, the question is, why did we did that? Well, observe that if we plug in negative infinity this time, we'll have this. So we have negative infinity, we raise it to 6. Then we have 5 minus 4 over negative infinity squared plus 3 over negative infinity raised to 6. And the good thing about this is that if we know that if we have constant over infinity, whether that is positive or negative, this just approaches 0. So this means that this out here, this 2 out here, becomes 0, and so is the other one. So that means that we'll just have out here, so this will just be infinity times a constant 5, or again, when we multiply a very big number to a constant, the outcome is still a very big number or infinity. So this one out here is our final answer. So I hope you got that one correctly. If not, that's fine, since especially this second one, it's quite tricky at first. But take note that this is a good trick that we can use. So this part, the factoring. And in fact, when we are dealing with limits at infinity of polynomials, so here's a remark. When we're dealing with limits at infinity of polynomials, we can just check the leading term. So in this case, we can just focus on 5x raised to 6, and we try to observe what happens when we plug in negative infinity out there. You observe that if we plug in negative infinity in just this one, we'll have infinity raised to 6, or count 5 infinity, or just infinity, which is the same as what we got. And the same for the first one. If we plug in positive infinity out here, we'll just have positive infinity squared, or just positive infinity, which is the same as what we got. So that is the trick when dealing with limits at infinity of polynomials. To end this, here's a nice exercise that you can work on. So technically, this is like a preview to the next video that we'll have. So in here, we are tasked to find the limit of 2x plus 4 over 5x as x approaches positive infinity. So yeah. Take note here that if we plug in x out here, we'll have infinity over infinity. Although we haven't discussed it, this one is actually an indeterminate form. Indeterminate form. There. Forgive my handwriting, it's not really nice. So yeah. So this is a nice exercise that you can try to work on. And if you want to learn how to solve this, stay in tune, as we will be discussing the indeterminate type form of infinity over infinity in the next video. So yeah, that's it. I hope you enjoyed and learned a lot from this one. Please don't hesitate to comment down below if you have any recommendations and suggestions in this video and in the channel in general. So yeah, again, that's it, and that's all for this video.